Hello everyone, my name is Rijul and I along with my friend Harsimran are here to present on the topic multivariate control charts. Before going on to the detail about what is multivariate control chart, first I have to tell you that nowadays we have to deal with processes with more than one correlated quality characteristics that are need to be monitored. Back then, a common practice was to control the stability of the process using univariate control charts, but there was some cons related to that. That is, it increases the probability of false alarm of special cause of variation. So, it should be performed through a multivariate approach. So, multivariate control charts are used to monitor two or more interrelated process variables. It helps to determine whether a process is stable as well as to monitor a process as new data are collected. Now moving on to multivariate normal distribution. Multivariate normal distribution is the core of multivariate statistical analysis. It exhibits approximately normality due to the central limit theorem. Normal distribution for univariate is given by this formula, and multivariate normal distribution is given by this formula. Here p is the number of random variables and it should be greater than equal to 2 for multivariate normal distribution, and mu is the p into 1 vector of the expected values, and sigma is given by p into p variance covariance matrix. There are various multivariate control charts, but the most common ones are the control ellipsoid one, the chi-square or the chi-square, the t-square or the Hotelling chart, the multivariate exponentially weighted moving average chart, the multivariate cumulative sum chart, and the chart based on the principal component analysis. So, my friend will explain them in detail. But before going into detail about them, there is a mult.chart function which is used to perform multivariate control chart in R. So here the function in function x must be a matrix or an array, and significance level is 0.01. And in mul.chart function it returns the value of t square statistics, the upper control limit, the sample covariance matrix, the mean vector, and if any point falls outside of the UCL and its decomposition. The multivariate control chart is also used to compute the most accepted and diversified continuous multivariate control chart like chi-squared one, Hotelling t-square.
So the first plot is the contour plot or the chi control chart. In multivariate normal distribution, the density is described by an ellipsoid centered at mean vector with axis in direction to the eigenvectors of the covariance matrix, setting mu as the origin. For making this chart or for making control ellipse, we need four things. The first one is mean vector xmv and the covariance matrix S. And here the another main thing is significance level, which is known as alpha, and the value for that is 0.01, and the eigenvalues and eigenvectors. For making this chart, we need to do a few things. First, we have to set the significance level, which is known as alpha, which we set like 0.01. Then with the help of that, then we find the mean vector and the covariance matrix. After computing those, we compute the eigenvalues and eigenvectors from which we can make an ellipse, and the direction of ellipsoid axis is given by the eigenvectors. So these two chart displays uh, the various the two types of ellipses. In first one, the confidence ellipse with the axis, and the second one is a scatter plot. So the main limitations of these are, because we aren't using a chi chart as now, so the main drawbacks are obtaining no points outside the ellipse, so there is no evidence of special causes, so which means the process is in control. But another difficulty to identify the points beyond the confidence ellipsoid is one of the main drawbacks. But the solutions for these two are either we should use the chi chart or we should insert the sample number in plot when the amount of point is not as large. So when we use the chi chart, so the equation becomes this. Before using this, the equation was just simple. There was a little bit change. In this equation, we just multiply this equation with n. So n is the sample size, and the upper control limit is chi square, which is dependent on alpha and p. Alpha is the significance level, and p is the number of random variables. And when we do that and we draw the plot for this after calculating the UCL value, what we get is this chart. We can clearly see the force sample value is really large as compared to UCL value, and is beyond it is out of control. So this makes this chart out of control. This is not a in control chart. So there are two phases for any chart, any multivariate chart. In the first phase, what we do is a retrospective analysis is applied to check if the process is in control since the first sample was collected. These studies are used when control charts are established for the first time and with the aim of bringing the process to statistical control. A deep understanding and analysis are required before the establishment of the in control state. And in phase 2, the control charts are employed to verify if the process remains in control. Here we here the process variability is monitored using the mean and covariance which we achieved in the phase 1. Then using the in control mean and covariance matrix, it is possible to control the future production. Then the next chart is Hotelling T-square control chart. So Hotelling procedure has become without a doubt the most applied in multivariate process controls. It is also known as multivariate Shewhart control chart. So based on the multivariate generalization of the statistic from the univariate normal theory, we get the t value as this. So after squaring, we can do the generalization from which the t-square values comes out almost similar to the previous chart value. So the for phase 1 and phase 2, while calculating UCL values, there is just a little bit difference. In phase 1, while calculating the value, we subtract 1 from the m, uh, where m is the number of samples taken from any data set, and n is the sample size, and p, as we know, is a number of variables. While for calculating phase 2, the UCL value, the we just add m 1 into m, so the other equation is almost same, and the denominator, which is mn minus m minus p plus 1, it represents the degree of freedom. So for phase 2, ये बीच में करना पड़ेगा. So we know if in a control chart one or more points fall outside of control limits, then there is a evidence that the process has suffered a non-random shift. In univariate alternative, the statistic proceeds from only one variable. But in multivariate problems, the identification of source that causes the out of control signal is more complex. So we know while calculating, we can clearly see that the force sample point is out of range. It is more than the UCL value. So what we do is we just first compute the t statistics, then we calculate the mean and variance, then we see if any value is going out way above more than the UCL value or not. If the value is a little bit large or more large than UCL value, then we just exclude it. Then we construct the t statistics again for the combinations of the remaining variables after excluding that. So in this chart, the force sample is out of control. The value is out of control. For that, so we will exclude the t-square values for x3 and the x4 and the x5, and x3, x4 and x5. But still we have to check for the values of t square for x3 and x5. Then the next chart is multivariate exponentially weighted moving average control chart, which is also known as MEWMA, MEWMA. So it is based on the principle of weighted average of observed vectors, and it is more sensible in detecting non-random changes in the processes. And this chart is mainly used for when the value of n is 1, which is for using individual observations. And it is also a chart for phase 2. So the t statistic values for this chart are as given. So where the z naught is 0 and alpha is diagonal p into p matrix with lambda value ranging from 0 and 1. But for the most popular value and the most prominent value used for this lambda is 0.1. So the exact covariance matrix is given by this equation, and the ARL performance of the chart depends only on non-centrality parameter theta, and the theta is given as this, where mu1 is the mean vector for phase 2, and when the value of lambda becomes 1, this chart get transformed into t square chart. And even for this chart, the main problems is one of the main problem is calculating the h or UCL value, and the other ones are the finding the value for lambda p and ARL. As we can see, there are only limited values for which we can go for, like for p values we can go from 2 to 10, and for lambda we usually go from 0 to 1, and most significantly we use zero point 0.1, and ARL we have only one value 200. Then the next chart is multivariate cumulative sum control chart, and this chart is an extension of the QSUM control chart, which is originally proposed by the Professor Page. It is focused on improving the sensitivity regarding the previously introduced t-square chart by detecting small shifts on the process, and it is based on the principle of accumulating information of the former observations as well as MUMA chart, and this chart is also a phase 2 chart. And for the better ARL performance we have two methods. For the first method is Crozier method, and the t statistics are given as this. And for this second method is the Pignatello and Runger method. And for this the t statistics are this. While calculating the t statistics in this case, we calculate the t maximum, t square maximum for every single observations, and we keep on doing for all the other remaining observations. So these are two charts which are made by using different methods. The first one is made by using the t statistics from the Crozier method, and the second one is from the Pignatello and Runger method. As we know, the we have to calculate the t square maximum in both cases. The problem is, after calculating that for one we have to again calculate we have to do the same procedure for all the values again and again. From these two charts we can clearly see that the Crozier chart provides a better sensitivity with a signal since the seventh sample. So here comes the last multivariate control chart, which is principal component analysis control chart. The PCA is a multivariate technique focused on the orthogonal transformation of a correlated dataset to obtain a linear combination of variables, which are known as principal components. Uh, the main aim is reducing the dimensionality, and for this, if x is a vector from 1 to p quality characteristics, and we have the eigenvalues which are in increasing order, like lambda 1 greater than lambda 2 equal to greater than lambda p. So then the linear combination which can we choose is like this, like the c1 is equal to e11 x1 plus e12 x2 until it goes on the pH value. And in these equations, Eij is the jth element from the ith eigenvector, and Cj represent the axis of new coordinate systems by rotating the original. This new axis represents the directions of maximum variability. The principal components are chosen by maximizing the variance as much as possible, and the variance of principal components is given by their eigenvalue, and proportion of the variance explained is given by this formula, lambda j divided by all the values of lambda from 1 to p. So there are many methods to decide the number of principal components. The score of the principal component Cj is determined by substituting the eigenvector values and the original observation of x1, x2 till pth value in each Cj. The use of PCA in multivariate charts is due to the feasibility of reducing the dimensionality of the regional dataset without a significant loss of information. So, Professor Jackson proposed three applications of PCA in control charts. First was the Hotelling chart applied to the principal component scores. The second one is control charts to the residual, and the third is univariate control chart for each score. But the main point is we will study only the first part. This is like if we give an example, like if we have a process with five or six quality characteristics and we study them, and after doing the PCA we find out that the first two or three components explain more than 80% of the total variability, and it can be controlled through 2D or 3D ellipsoid. So the for phase one, while drawing the charts for chi-square and Hotelling charts, we get these charts, and even if we go for phase two, the confidence ellipses in phase one and phase two are almost same. Not a single value is going outside. So all the points are inside the confidence ellipsoid, and even for the finding the value for chi-square and Hotelling charts, oh sorry, we can see that only in the case of phase 2, only single value, it is almost like 18 sample value, it is going way above than usual value. So we can say that due to just 18 sample value, this chart is going out of control. But as we studied earlier, that we can find this sample and we can exclude this sample from our data set, and then again we can calculate the t-square statistics after excluding the value, and for all the remaining values we can again come up with a more better charts which are in control. So while after calculating in the output of the t-chart, the source of variability is associated to the principal components. So this way we can use various multivariate control charts to our dataset to have our process in control and to get the maximum information from them. Thank you.